Welcome to Anatomic Structures. Thanks for coming back. Thanks for viewing my 4 viewers, 2 of which are me. Totally cool with that though. I'm not YouTube famous yet. But we are going to work on several collections here, trying to understand the periodic table and atomic structures. So enjoy. Hey, here we are, taking a look at our activity for the week, having to do with the periodic table, electron configuration. So I've opened up our website. I have not taken a look at this yet, so I'm actually going to read through it and then step back in. So hang tight. This closer so that we can see this a little bit better, because as you can see, the lighting is terrible. But we are looking at data collection number 1, where we are asked to evaluate magnesium on our periodic table under this program. So we're going to go ahead and select magnesium, and then this is going to give us our energy diagram here, and we're asked to then sketch that on our paperwork, and then go ahead and assess how the energy level and the orbitals are related. So I'm going to go ahead, and we've got magnesium here. I've already documented how this would look, and so since magnesium, the periodic table, if we take a look at this, we've got 12 here. So our energy is 2 in 1s, 2 in 2s. So that fills that orbital completely. And 2p is completely full as well. And then the remaining 2 electrons fall onto the 3s orbital. So then we'll go down here and evaluate how that energy level relates to the orbitals. Part 2 asks us to speculate why there are more orbitals at higher energy levels, and to consider the geometry of the atom in a 3-dimensional space as you get further away from the nucleus. I'm speculating that there are more orbitals with higher energy because there are more electrons, and electrons are kind of selfish, is I think a good way to describe them. They like their space and they need a lot of it. They're very active. So when considering the geometry of an atom in a 3-dimensional space, as you get further away from the nucleus, again, these electrons are selfish and they require a lot more space. So they move out, and they don't like each other. They repel each other. So the further out, because they're excitable and because they don't like to be next to one another. Close space is not their thing. So I'm going to go ahead and document these speculations, and I am then going to move on to the next part. So hang tight. All right, thanks for sticking by. We're going to look at data collection 3. So in here, we're asked to go ahead and use our program to evaluate hydrogen and helium, and then to go ahead and document and sketch what that diagram is going to look like. So I'm quickly going to do that. We'll start with hydrogen. And as we can see here, let me bring you a little closer. Hey, love the close-ups. I know it's backwards. We've got the frontal camera working here for functionality, but as you can see, there is one arrow in 1S here. So we'll go ahead and document that real quick and move on to helium, and we'll go back to the periodic table and select helium, and we see that there are two arrows in energy level 1S, so we'll go ahead and graph and document that. In section 4, we're asked to go ahead and describe some of the explanations on what these symbols are meaning, what these diagrams are trying to represent. I'm going to go ahead and take a moment to review the questions and postulate my understanding, and hang tight because we will be back to take a look at the next section. Ooh, my Roman numerals, I gotta think about it. Section 6, we're looking at data collection number 6, and it's asked us to go ahead and display lithium, which I have, and I'll take you closer. Again, it will be backwards, but I think you'll get the general sense here of what we're doing. And so we're then asked to predict what we think the next orbital will look like for beryllium. I anticipate that it will fill 2S since it is open. So we're going to go ahead and click the next button here, right here, and look at that. And we will move into data analysis and interpretation, which is asking us to kind of express our understanding of why this is happening. Hang tight, we'll be right back. Section 8, and it has asked us to pull up boron here, and we've done that. And then to go ahead and sketch it, and then anticipate what the next element is going to look like, which is carbon. And so I've gone ahead and documented my expectation. I don't anticipate that it's going to fill the first 2P. I anticipate that it's actually, since there are 3 boxes on our diagram, I'm anticipating it's going to spread out before it starts duplicating back over. That's my expectation, so we will find out by hitting the next button. Are you ready for it? Here we go, and oh, believe it or not, my expectation was on point. So our data analysis and interpretation has asked us to speculate why for boron the diagram orbitals have different energies, and then to also evaluate carbon and describe why we feel that instead of doubling up, it actually spread out into the p orbital. So we'll go ahead and answer those questions. So, section 10 is making some conclusions here and asks you to predict the energy and orbitals for nitrogen, which I have gone ahead and done right here. And then we continue by looking at the remaining atoms in the row: oxygen, fluoride, and neon. And so I've gone ahead and made my predictions, and I went ahead and double checked that I was on point, following my previous expectation that orbitals will fill first in the down direction. For example, 2p would be down direction times 3 before coming back and doubling back over into filling again the first of 3, the second of 3, and the third of 3. So we're then asked to express our understanding and then to predict where the 11th electron for sodium will be placed and to sketch that. So I'm going to go ahead and sketch that out, answer those questions, and we'll be back. This is like periodic table soap opera. Are you ready for it? All right, it's about to get interesting. Are you ready for it? So, major close-up right there. Data collection 11 is asking us to hit the next button from sodium to argon. So we're gonna go ahead and do that. And we're gonna watch what happens. It's about to get really interesting. So here is sodium. As you can see, we've got, don't touch it, this is touchscreen. We have a representation in 3s for sodium. That's where our electron has landed. So our next atom, magnesium, fills 3s. But as you see here, we have 3p, 3d. So this is getting a little bit more interesting right in here. Curious to see what we're going to observe. So magnesium to aluminum. Sulfur. Oh, we had already filled out 3p in the first downward direction, so we looped back over and filled up that first one here. Chloride landing right here. So this guy is unaccounted for, this poor little guy right here. Oh, there we go, argon. So we are completely full. Also following the idea that that last column is the most stable column on our periodic table. Everything is full, it is happy, it is content, and all atoms try to accomplish that. They try to obtain harmony, if you think of it that way. The collection 13, we're asked to look at potassium, which I have displayed here, and to go ahead and record observations from potassium to validinum. I may not have said that right. So we're going to go ahead and evaluate what is going to happen. So if we are at potassium, I'm expecting that we're going to fill S. And then I think we're going to be a little surprised that we're not going to follow numerically. So let's check it out. Potassium, calcium. Oh, hold on. Did you see it? 4s fills up with calcium. And then our next electron fills the first orbital in the downward position at 3d. We're not even there yet. Here we go. Do you think it's going to fill this one? Nah, I think it'll follow suit and go here to this next one. Let's see. There we go. Oh, check it out. Check it out. I'm going to draw attention here to 4S and 3D. At a quick glance here, they look equal, and you're thinking, wait a minute, is this making sense? And it is. So if you see here, I'm using this pencil to kind of draw a connection between 4S orbital and 3D orbital and how it's displayed here in this program. And so you see that, is this energy equal? Possibly. But we know that our S orbital has a geometry in and of itself, and that the D orbital has a geometry in and of itself, just as the P orbital does. So, fun fact, this here, this area here, mixes things up. It's not numeric. It's not even alphabetic. You truly have to understand what is going on here. We're going to have to overcome some functional difficulties here, but we'll move on. We'll get through this. So as you can see here, this is where we left off, and our next step is to go ahead and predict what chromium is going to look like. And looking at this here, I'm going, I mean, do we go ahead and fill another 3D? I feel like this is where it's going to go. So let's just see what we get. Oh, okay, hold on. I feel like we've got to... All right, look at this here. Wait a minute. So 4S is no longer filled. Okay. And 3D is completely filled. So logically thinking about this, okay, this is sensible. If we follow how all of these other orbits filled, they always filled horizontally in the down position first before looping back around and filling the upward direction. So it looks like 4S, the electron here that was in the upward direction, goes ahead and fills one of these open downward positions in order to fill this entire area here, this entire section in the downward position. Interesting. I mean, did you see this? Hold on. Did you see this? Okay, here we have it full. Hit next. And it literally moves. Look at that. It literally moved across the screen. We are asked to go ahead and follow chromium through nickel and see what happens in our orbitals and energy here. So I've got it set up where we are where we left off. Our first layer here of the downward direction between 4S and 3D are completely full. So we're going to go ahead and continue through until nickel. Watch closely, because I feel like this is going to trip us up. I mean, it's already done it once. Yep. Okay, so that makes sense. We went in the upward direction in 4S. Iron. We went over to 3D in the upward direction. Again, in the upward direction. Nickel, upward direction. Oh, they did not trip us up. All right, chemistry, making it interesting. Hold on. The next step is to look at what happens when we move from nickel to copper. Currently, this is where we stand. Did you see that? Okay, chemistry. Now, 4s has an open orbital here, and 3d is completely full. All right, I'm honestly not really sure how to make any predictions at this point. I'm a little tripped up. But we're going to continue and press forward. So here we have copper. And we're asked to go ahead and click the next button until we get to zinc. Okay, here we go. Okay. Whew. I can breathe. All right, so that last electron seems to have filled 4s when we got to zinc.